Hi everyone, Happy New Year. Welcome back to Chem Help ASAP. It's a new year, it's time for more live streams. So I know we're early in January, and so most of the colleges and universities probably aren't quite in session yet, but I know that many high schools, at least in the US, have either started or getting started. So I thought I'd start with the new year with some basic concepts. So that's why we are going to be balancing chemical equations. And I'll show you, first we'll talk about why we need to balance chemical equations, and then I'll show you some tips and tricks to help you balance, especially those more difficult chemical equations. As always, if you have questions, please send them over to the chat. And it looks like OG Benchmarks is saying there is a little bit of buzz in my audio. So I'll just make sure that all of my connections are good, and hopefully that fixes everything. OG Benchmarks, let me know. Okay, great, it's fixed. Okay, so let's get started with balancing chemical equations. All right, so first I'm going to use this example of water just to explain why we need to balance chemical equations in the first place. So you might think, well, we have our reactants, we have our products, who cares if it's balanced or not? We know what we're starting with, we know what we're ending with. But this helps us predict maybe how much product we're going to get, or maybe how much of a reactant we need to make a specific amount of product. So I liken this to when you're making cookies for a party. You need to know how many cookies a recipe makes so that you can know how many recipes to make. But let's talk about this first equation right here. Okay, so let me switch over to here. So we simply have water, and we are breaking it down into its elements, hydrogen and oxygen. Now, of course, in its elemental form, both hydrogen and oxygen are diatomic molecules. So what I think the best way to illustrate this is to actually draw the molecules. So let's draw oxygen as blue, and then let's draw our hydrogens here as green. So here is water, 2 hydrogens and 1 oxygen. So initially you might think, well, let's just break this apart, and we can certainly form our H2 here. But then what we've got left over is we just have 1 oxygen. So 1 molecule of water will not break apart and give us our diatomic hydrogen and our diatomic oxygen. Of course, what we need is 2 molecules of water. So if I bring another molecule of water over here, again, 1 oxygen, 2 hydrogen. What I can do is I can form, oh yes, I do want to stay with green, another hydrogen here. And now I've got another oxygen. And these 2 oxygens can then bond. So let's maybe, I'm going to rewrite these as an oxygen molecule, like so. Okay, so this is why we balance chemical equations, because it lets us keep track of our atoms. So we know how many atoms we start with and how many atoms we finish with are the same. So we cannot create or destroy atoms in a chemical equation. Now we can break bonds and reform new bonds, and that's totally fine, but we are not going to create or destroy atoms. So I am not going to draw out the molecules for each of these chemical reactions. What we do is we balance with what's called stoichiometric coefficients. And what that means is, actually let's stick with blue here, I'm going to put numbers in front of all of my molecules and my reactants and my products to denote how many of those molecules I need. So you can see for my reactants, for my water, I had 1, 2, that's a 2 molecules of water, so I should put a 2 here. For my hydrogen, I got 2 molecules of hydrogen, so there is a 2 here. And of course, I only got 1 molecule of oxygen. Now, you can write a 1 here, but generally we just leave it blank. So if it's left blank, we assume that there is a 1 there. Okay, so the other way that we do this, instead of having to draw everything out, is I like to create a table of what atoms are on the reactant side and what atoms are on the product side. So I'll show you how I do this again with this same water example, and then we'll move on to other examples. Okay, so let's maybe switch to black. So on my reactant side, I have hydrogen atoms and I have oxygen atoms. Now I'm going to count up how many I have just on the reactant side, so I keep my two sides separate. So for my hydrogen atoms, I have 2 because there's a subscript 2. And of course for my oxygen atoms, again, we don't write the 1, so there's just 1 oxygen atom. Now on my product side, I still have hydrogens and oxygens. Again, you're not going to create or destroy an atom in a chemical equation, so you should have the same types of atoms in the reactants on the reactant side and the product side. If you don't, something is wrong with the reaction. Okay, so initially I have 2 hydrogen atoms, and you can see I have 2 oxygen atoms. Now, what hopefully you see at this point is that while our hydrogen atoms are balanced, they're the same on each side, my oxygen atoms are not balanced. So if I put a multiplier in, like I just did here with my atoms of 2, what that does is that changes this 1 now to a 2, and it changes that 2 to a 4. Again, 2 times 2 is 4. It's a multiplier, so anytime you have a stoichiometric coefficient, it multiplies to all of the atoms within that molecule. Okay, and so what this does, of course, is it helps balance my oxygen. So now my oxygens are balanced. However, it does make my hydrogens unbalanced. Now this back and forth is totally normal. So don't be afraid to balance one atom, even though you know it may unbalance another atom. That's completely normal. It happens a lot. We'll see it multiple times over. Because of course, what I can do with my hydrogen on my product side is what I did up here is put a 2. That's a multiplier. That changes it to 4. So now you can see I have 4 hydrogens on my reactant side. I have 4 hydrogens on my product side. I have 2 oxygens on my reactant side, and I have 2 oxygens on my product side. So this is kind of 2 different ways to think about how we balance equations. We really are keeping track of atoms. If you need help with this, sometimes it helps to make molecular models. If you have a modeling kit, that can help initially with just keeping track of atoms. But also just when you're doing it on paper, I find kind of making this table makes it very easy to keep track of atoms and keep track of which atoms are balanced on reactant side and product side. Okay, so let's move on to our second example here. With sulfur and oxygen going to sulfur dioxide. So again, I'm just going to list out the atoms on my reactant side. So I have sulfur and I have oxygen. I have 1 sulfur atom on my reactant side, and I have 2 oxygen atoms on my reactant side. And on my product side, I also have sulfur and oxygen. And if I count them up, I have 1 sulfur atom and 2 oxygen atoms. So this is kind of the situation that we're always hoping for. You can see my sulfur atoms are balanced and my oxygen atoms are balanced. This equation is already balanced. It is a 1-to-1 stoichiometric ratio between the reactants and the products. You always want to check though. Don't just look at a reaction and assume it's a 1-to-1. You need to count up your atoms and make sure it's a 1-to-1. But these are the ones that we actually hope for. But let's move on to some other ones that are not necessarily 1-to-1. So here are 2 different reactions. I'm going to work the left one first and then I'll work the right one. And let me just make sure that, yes, you can see that second reaction. I know that my video feed kind of can interfere with that. So I'm going to start with this aluminum example right here. Again, I am just going to list the atoms that I have on my reactant side. So I have aluminum. I also have hydrogen. And I've got chlorine. So let's count up how many we have of this. We have 1 aluminum, 1 hydrogen, and 1 chlorine. Okay, so for my product side, I also have aluminum. Just to keep this consistent across, I'm going to go ahead and write hydrogen here. But you can write it however you want, however it makes the most sense to you. It's easier for me to compare across if I keep them in the same order. So for my product side, I have 1 aluminum, I have 2 hydrogen, and I have 3 chlorine. Okay, so as a general rule, if you have hydrogen and oxygen, especially when they're in their elemental form, meaning you have H2 or you have O2, it can be best to wait and balance those last. So this is just kind of a general tip. I'll write it down here. I'll say balance hydrogen and or oxygen last. You don't have to, but often I find it easier to balance the other atoms first. So in this case, as I'm looking, I can see my aluminums are the same. Again, I'm going to hold off on my hydrogens. So let's balance my chlorines first. So in order to make these numbers the same, again, I need to use multiplier, so I'm not adding or subtracting. I am going to put a 3 in front of the hydrochloric acid. Now this changes both the hydrogen and the chlorine. So it changes the chlorine to 3, which is great, and it changes my hydrogen to 3, which is also, helpful to know. So now if I'm looking at what's balanced, my aluminums are balanced, my chlorines are balanced, but my hydrogens are not balanced. Now in this situation, I've got a little bit of a difficulty because there is no multiplier unless we're going to use a fraction to make a 3 equal to a 2 or 2 equal to a 3. So what I'm going to do is I'm going to help myself a little bit, and I am going to multiply through by 2. And what I mean by that is I'm going to put a 2 right here. So I'm multiplying my hydrogen more specifically by 2, but you'll see I'll end up multiplying everything by 2. And what that does is, oh, sorry, this should not be a 2. See, I'm not even thinking straight. I meant to multiply this one by 2 to make this 6 instead of 3. Again, with these kind of balancing equations, you'll find that if you are working next to a friend, that your friend might be balancing it in a little bit different way. It's totally fine. You just need to try something at first and see if it works. So I often find that multiplying by 2 can help. Or you can think of this also as, since you have a 3 and a 2 here, you can think of multiplying this side by 2 and this side by 3. That is also another way that this can work. Okay, so let's go back here. So if I have changed this to a 6, that means now I have 6 hydrogen, but I also have 6 chlorine. So you can see I've changed chlorine now twice. Again, totally fine. You can change it as many times as you want. So in order to make this balanced at this point, I have 6 hydrogen on my reactant side. I have 2 on my product side, which means if I multiply here by a 3, that changes that to 6. All right, so hydrogen is now fixed. Let me see if I can fix my chlorines. So I have 6 chlorines on my reactant side. I need to make this 6 on my product side, but again, this is pretty easy. I just need a multiplier of 2. That changes it to 6, but now this has also changed my aluminum. So my aluminum has been the same the whole time, but now I have changed it to 2, so I need to finally go back and fix my aluminum because now I have 2 on my product side. I still only have 1 on my reactant side. But if I put a 2 here, you can see that changes it to a 2. So I like this example because you can see I went back and forth a number of times. And again, there are a couple different ways to tackle this problem. So don't ever be afraid to balance one atom, even though you think, oh, but that's gonna, make my hydrogens messed up, or that's gonna mess up my aluminums. Go ahead and balance whatever atom you're focused on right then go back and see if you can rebalance the one that got unbalanced. Another tip I will give is sometimes with these more complex ones like this, where you're back and forth and you're back and forth and you're doing a lot of changes. If you feel like you're stuck in a loop and you keep making the same mistake, sometimes it's best to just erase everything and start fresh. Another thing that you can do, especially if you have created this equation either by reading the names of molecules or you have done your own predicting products, make sure that you have the right molecules as the reactants and the products. Because if they're not set up, like if you haven't done your ionic, your name to your molecular formula correctly, that's going to make balancing just impossible. Okay, so let's make sure there are no questions here. That was a little bit of a rabbit trail that I went off on. Let's do our second example on this page. So we have sulfuric acid reacting with lithium hydroxide to give us lithium sulfate and water. So again, I'm just going to list out my atoms. Now this one is going to be more complex because I have atoms that are in multiple molecules. Okay, so I have hydrogen, I have sulfur, I have oxygen, and then over here I have lithium. I've already listed oxygen, but you can see oxygen is in both molecules. I need to make sure I add the oxygen from both of those molecules together. And the same for the hydrogen. So this is my list of atoms, but I just need to make sure that I'm adding up, for example, all of my oxygen atoms. Okay, so let's go ahead and do this. So for hydrogen, I have 2 hydrogen atoms from sulfuric acid and 1 hydrogen atom from lithium hydroxide. So I have 3 total hydrogen atoms. For sulfur, I just have 1. For oxygen, I have 4 from sulfuric acid and 1 from lithium hydroxide. So I have 5 oxygen atoms, and of course lithium, I just have 1. So I'm going to do the same thing on the product side. And again, I like to list my atoms in the same order just so that I can compare across, but you don't have to do that. So I'm going to go hydrogen, sulfur, oxygen, and lithium. And again, you might list your atoms in a completely different order just from the get-go. That's totally fine. Okay, so hydrogen, on my product side, I only have hydrogen in my water, so that makes it easy. I have 2. For sulfur, I only have 1 in my lithium sulfate. For oxygen, I need to make sure I add up both the 4 from the lithium sulfate and the 1 from water, so I have 5. And then lithium atoms, I have 2. Okay, so again, just like the rule I gave you before, not really the rule, kind of the tip, I'm going to wait and balance hydrogen and oxygen towards the end. So basically, I'm going to wait to balance this water towards the end. So I want to balance my other atoms first. Well, sulfur is already balanced, so that's great. So I'm actually going to work on my lithiums first. So I have 1 on my reactant side and 2 on my product side. So I'm going to put a 2 here in front of my lithium hydroxide. Okay, so this changes a couple of my atoms. First, it changes my lithium. I now have 2. But again, remember, this multiplies to all of the atoms in this molecule. So it applies to the oxygen and the hydrogen. So now I have 1 more oxygen atom. Now we have to be careful. The temptation is to take this 5 and make it 10 because you multiply by 2, but that is not actually what you have. Oops, let me erase this line. You still have your 4 oxygen atoms from your sulfuric acid, but now instead of just adding 1 oxygen atom from your lithium hydroxide, you need to add 2 because now we have 2 oxygen atoms from our lithium hydroxide. So this is no longer 5, but it is 6. The same thing happens with our hydrogen. We still have the 2 from sulfuric acid, but now I have 2 more from lithium hydroxide because I have this multiplier, which means I have 4 atoms there. All right, so let's go back and let's see what we got going on. Okay, so sulfurs are still balanced, lithiums are balanced, so it is time to deal with oxygen and hydrogen. And ideally, I'm going to balance these by just putting some kind of multiplier in front of water. I really would rather not put something in front of lithium sulfate at this point because it's going to change my lithiums and my sulfur. So if I can avoid that, that's great. That's what I'm going to try and do. But again, I might not be able to, and then I'm just going to have to go back and rebalance. Okay, so at this point, I have 4 hydrogens on my reactant side and 2 on my product side. Okay, so just looking at hydrogens, I'm thinking, what if I put a 2 in front of here? But let me look at my oxygens as well. So right now I've got 6 on my reactant side and 5 on my product side. So if I put a 2 in front of here, that should actually give me 6 oxygens. So let's put a 2. And let's just count up atoms. Again, remember this 2 multiplies to the hydrogen and it multiplies to the oxygen here. Okay, so for my hydrogen, I now have 2 times 2. I have 4 hydrogen atoms. And for my oxygen, so I still have my 4 from my lithium sulfate, but now I need to add 2 more because I have a multiplier of 2, which is going to give me 4, 5, 6. And that's all it changes. And you can see that my atoms are now balanced, and this is 6 and 6, and I have 2 lithiums on both sides. So this was one that feels like it should be really difficult because I have a lot of atoms and I had oxygen and hydrogen in both of them, but actually this one turned out to be simpler, I think, than the one on the left-hand side. Okay, let's go ahead and do our next examples. And again, I want to make sure that, okay, that one, you can see the one on the right a little bit better. Okay, so we've got iron and oxygen reacting on my left-hand side reaction. So let's work through this one. So again, just listing out my atoms. For my reactant side, I have iron and oxygen. So I have 1 iron atom and I have 2 oxygen atoms. That's nice and easy. And for my product side, still just iron and oxygen. I have 2 iron atoms and 3 oxygen atoms. Okay, so let's work on balancing. Per usual, I'm going to try to balance oxygen last. So let's see where that gets us. So if I'm going to wait on oxygen, I have 2 irons on my product side. I have 1 iron on my reactant side. So let's go ahead and put a 2 in front of here. And that balances my iron atoms. Okay, that's great. It actually didn't help with my oxygens at all. Again, I've got a 2 to 3 ratio here, which is a little bit awkward. But what I'm going to do is I'm going to multiply each side by the opposite. So I'll show you what I mean by that. So because I have 3 oxygens on my product side, I'm actually going to multiply by 3 here, and I have 2 over here like this. So what you can see that does is now I have 3 times 2, I have 6 oxygen atoms on my reactant side. And now I have 2, of course it does multiply to the iron, but I'm just talking about oxygen. I have 2 times 3, which also gives me 6. So now I've got my oxygen atoms are balanced, but of course I have messed up my iron because I now have a multiplier of 2, which means I now have 4 iron atoms on my product side, and I need to fix that with my reactant side. So instead of this 2 here, I'm just going to erase. And now I need a 4. And that changes this to 4. So again, you can see it's back and forth, and I had to do a little bit of erasing. I thought maybe a 2 was going to go there, but I was wrong. It needed to be a 4. This is, again, totally normal. Go back and forth. You're going to do some erasing. That's fine. It doesn't mean you're doing it wrong at all. Okay, let's do our reaction here on the right. Again, I am listing out my atoms. I've got calcium, I've got hydrogen, and I've got oxygen. So I have 1 calcium atom, 2 hydrogen atoms, and 1 oxygen atom. And then on the product side, calcium, hydrogen, and oxygen. I need to be careful with hydrogen here because it's in 2 places. So this 2 here is going to multiply to what's inside the parentheses only. It does not multiply to the calcium. It just multiplies to the oxygen and the hydrogen. So a subscripted number is only going to multiply to either the atom directly in front if there are no parentheses, and if there are parentheses, it only multiplies within those parentheses. However, a number in front of a molecule, what we call a stoichiometric number, that multiplies to all atoms in the molecule. So one part of balancing is knowing how each of these multipliers works. Okay, so for calcium, I do have just 1 atom. For hydrogen, I have 2 atoms from my calcium hydroxide plus my 2 atoms from my elemental hydrogen right here. So I have a total of 4 hydrogen atoms. And for oxygen, again, it is multiplied by 2. So I have 2 oxygen atoms right there. Okay, so let's see. My calciums are already balanced. Sorry, I forgot my colon there. My calciums are balanced, my hydrogens are not balanced, and my oxygens are not balanced. So, you know, I can balance either one. It doesn't really make a difference. I guess I'm going to go with oxygen first. Why not? So if I have 2 oxygen over here and 1 over here, I'm going to put a 2 right here. So this changes both my hydrogen and oxygen. Again, it's going to multiply to my hydrogen and to my oxygen. So I now have 4 hydrogen atoms and I have 2 oxygen atoms. So that's all great. And you can see that this actually helped me out with balancing my hydrogens as well. So now I have 4 hydrogens on both sides. I have 2 oxygens. My calciums are already balanced, and this equation is totally balanced. So again, sometimes you look at an equation and you think, oh, this is simple, this is going to be easy to balance, and sometimes those tend to be the more difficult ones, and sometimes the ones that look more difficult tend to be the easier ones. Okay, so let's move on to some more balancing equations here. All right, so this is a really long one. I'm actually going to show you 2 different ways to balance this. So I'm going to go through the atoms first, and then I'll show you a little bit of a shortcut and let you know when that shortcut can apply. So I have calcium chromate and sodium chlorate, and that's giving me sodium chromate and calcium chlorate. So this is an example of a double replacement reaction. But let's just list out our atoms here. So we've got a lot, which is why I gave myself one whole page. We've got calcium, we've got chromium, we have oxygen. Again, oxygen's in all 4 of our molecules here. So we're going to have to be really careful with oxygen and counting those up right. We also have sodium and chlorine. And then, of course, oxygen's already taken care of here. So let's count up atoms. I have 1 calcium, 1 chromium. Okay, so oxygens. I have 4 from calcium chromate and 3 from sodium chlorate. So I have 7 total oxygen atoms. Sodium, I just have 1, and chlorine, I just have 1. So let me go to my product side. Again, I'm going to keep everything in the same order as my reactant side. Sodium and chlorine. Again, make sure you haven't created any atoms. This is not nuclear chemistry, not yet. It's just chemical equations. Okay, so let's count up. Calcium, I have 1. Chromium, I have 1. Oxygen, okay, I got to be careful. So I've got 4 for my sodium chromate, but remember this 2 multiplies to the oxygen and the chlorine. It does not multiply to the calcium. So I have 4 oxygen here and 3, I've got 6, so I have a total of 10 oxygen atoms. Sodium, I have 2, and chlorine, I also have 2. Again, I'm going to try to balance my oxygens last, and I'm also going to hope that in balancing my other atoms, maybe my oxygen atoms will work out on their own like they did in the previous example. So just looking at my list here, okay, so my calciums are good, my chromiums are good. Again, I'm skipping oxygen for now. My sodiums and my chlorines can use a little bit of help. So let's fix sodium first. So to give myself 2 sodium atoms on reactant side, I'm going to put a 2 in front of here. Okay, so that changes sodium to 2, but it also changes my chlorine. That goes to 2, and it also changes my oxygen. So I'm gonna have to add these up again. I still just have 4 for my calcium chromate. But now, because this 2, again, it multiplies to all 3 of these atoms, I have 6, which means I have 10 oxygen atoms. And you can see that what I've done here is I've actually finished balancing everything right here. Okay, so this is beautiful. Again, you look at this and think it's complex, but it's actually pretty simple. Now let me show you a different way to balance this. Now this one tended to be easier than we thought, but let me show you an even simpler way. So what I notice in this reaction, this is a double replacement reaction. So my polyatomic ions, my chromate, you see my chromate from my reactant to my product side stays exactly the same. So I haven't changed it from chromate to dichromate or anything like that. It's exactly the same, which means I can balance chromate as one unit. I can do the same thing with my chlorate. See how my chlorate stays the same? It doesn't become chlorite. It doesn't become perchlorate. It stays chlorate, which means I can keep that as a unit. And I'll show you what I mean by that. Let me do this in a different color. So instead of listing out all my atoms, I'm thinking of this more as listing out my units. So I have my calcium atom, that stays the same, but I'm going to keep my chromate as a unit. So I'm going to list chromate as something to balance. And the same thing over here. So my sodium, you can also think of this as listing your cations and your anions, because again, they don't change from reactant side to product side. So I have my sodium cation and I have my chlorate anion. Again, I'm going to keep this as a unit, and I'm going to do the same thing on the product side. So I have calcium, I have chromate. Again, it doesn't change, so I can balance it as a unit. Sodium and chlorate. So if I look for calcium, I have 1. For my chromate, I have 1 chromate. Sodiums, again, I have 1. And chlorates, I have 1. So I have 1 of each on my reactant side. Again, this is assuming I don't have this 2 here right now. So for, again, calcium on this side, I have 1. For chromates, I just have 1. For sodium, I have 2. And you can see for chlorate, it's got a multiplier here of 2, so I have 2 chlorate anions. So what you can see is this is going to lead me to the exact same equation that I've actually already written here. So you can see my calciums are balanced, my chromates are balanced, but my sodiums and my chlorates are not balanced. But by putting my 2 here, which of course I did in my previous method, what that does is it changes the sodium to 2 and it changes the chlorates to 2, and my equation is now balanced. So this is really handy when you have polyatomic ions, because they tend to be large, they tend to have oxygen in them, which means you're doing a lot of adding up of oxygen for all these molecules. So if your polyatomic ions stay consistent from reactant side to product side, and that really is the key, because if you take a polyatomic ion and you break those bonds, then this trick will not work. But if they stay the same from reactant to product, you can balance them as units, which helps make your life a lot easier. Okay, let's go on to another one. Again, we're going to balance this first by atoms, but then we're going to balance it using polyatomic ions. Okay, so I have lithium acetate, ammonium phosphate, going to ammonium acetate and lithium phosphate. So again, this is another double replacement, and I'm going to balance by atoms first, then I'm going to balance by polyatomic ions. So let's balance by atoms first. It's going to take a little bit longer. So I have lithium, I've got carbon, I have hydrogen and oxygen, I have nitrogen, hydrogen I've already taken into account, phosphorus, and oxygen I already have right here. Okay, so let's do the same thing on the product side. Calcium, hydrogen, oxygen, nitrogen, and phosphorus. Okay, so, oops, I forgot to count everything up. Okay, lithium, 1. Carbon atoms, I have 2. Hydrogen, okay, this is going to be a little bit tricky. I have 3 here, and remember, this multiplier, it multiplies to the hydrogen and to the nitrogen, so I have 12 and 3, which is 15. Oxygen, also a little tricky because I have oxygen from my acetate and oxygen from my phosphate. So I have 2 here, sorry, and 4 from my phosphate, which means I have 6. And my nitrogen, I've got my multiplier, that's 3, and phosphorus, I have 1. Okay, so on my product side, lithium, I've got 3. Carbon, I have 2. Hydrogen, I have 3 here and 4 here, so I have 7. Oxygen, I have 2 here and 4 here, so I have 6. Nitrogen, I just have the 1, and phosphorus, I just have the 1. Again, I'm going to try and save my hydrogen and oxygen for the end. I'm going to try to balance my other atoms first. Okay, so, you know, lithium is right here. It's unbalanced. I'm going to go ahead and balance lithium first. So if I have 3 lithium over here and I just have 1 on my reactant side, let's put a 3 here. All right, that's going to make some changes. This now has 3. My carbon is now 6. Okay, so my hydrogen has changed. I now have 9 plus 12 is 21. For oxygen, I have 6 and for, that's 10. For nitrogen, okay, nitrogen hasn't changed. That is all of them. And my phosphorus also has not changed. Okay, whew. All right. So now at least my lithium is balanced, and you know, that's good. I am gonna go for, I'd really rather not go for an atom in acetate right now. I'm going to go for my nitrogens because my nitrogens stay within my ammonia. So I'm going to try for my nitrogens next. Again, you can see how this is a very individualized process. You can balance whichever atom you want to start with whatever atom you want, go to the next one that you feel is going to be easiest. And that depends on how you think through these problems, and that depends on the problem itself. So for me, I'm thinking, you know what, I think I want to balance nitrogen next. I think that's actually going to be easiest. So I have 3 nitrogen on my reactant side, I have 1 on my product side. So I am going to put a 3 right here. Okay, so that's going to change a lot of things. First, it's going to change my nitrogen. I have 3. Now it's going to change my hydrogen. I have 12 there, plus 9 there, well, which is 21. Okay, so yay for that. Carbons, I now have 3 times 2 is 6. And oxygens, I have 3 times 2, which is 6, plus a 4 here, which is 10. Okay, so you can see my instinct to go with nitrogen next actually really helped me out because I now have a balanced chemical equation. Okay, so how does this work if we're going to keep this in polyatomic ions? And I will show you, and it's actually a lot easier. So what you can see is my acetate anion here is exactly the same reactant side and product side, so I can balance that as a unit. The same is true of my ammonium cation. That stays ammonium on my reactant side and ammonium on my product side, so that can also be balanced as a unit. And phosphate as well can be balanced as a unit because it's the same on reactant side and product side. So this time, instead of listing out all my atoms, I'm going to list out again what I consider my units that I'm going to balance. So lithium is still on its own, but now I'm going to list acetate as a whole unit. And that's way easier because acetate has carbon, hydrogen, and oxygen. Okay, and then I have my ammonium cation, okay, and I have my phosphate anion. So let's see how many of these we have. So I have, again, ignore my blue numbers for now, pretend we've still got a blank blank equation here that's not balanced, excuse me. So for lithiums, I would have 1. For acetates, I had 1. For ammoniums, I would have 3, and phosphates, I would have 1. So same thing on the product side. Again, I'm going to keep it in the same order. Acetate, ammonium, and phosphate. Okay, so lithiums, you can see I've got 3. Acetate stayed the same, I just have 1. Ammonium, I also just have 1. And phosphate, I also have 1. All right, so you can see at this point now in my green list, I've got a bunch of 1s and 3s. So to balance, I'm just going to be multiplying by 3. So to balance my lithiums here, again, I'd put a 3 right here, which is exactly what I did. So what that does is that gives me 3 lithiums, and it gives me 3 acetates. So now if I wanted to, say, balance my acetates, then I'd say, oh, I need to put a 3 here to make this 3 acetates. So again, I'd put a 3 right here. That makes this 3 acetates, and it makes this 3 ammonia. And so now I have a balanced chemical equation. So again, wherever possible, it's nice to be able to balance polyatomic ions as just a unit instead of counting up all those hydrogens and oxygens, because that can take a while, and it's also easy to make a mistake. When you have especially oxygen in multiple molecules, it's easy to add those up wrong, and then you think you don't have a balanced equation when actually you do. Okay, let's move on. We've got time for some more. Okay, so this is a combustion reaction, and combustion reactions are notoriously difficult. So I'm going to show you, again, 2 different ways to balance this equation. So let's start by just the way we always do. Let's list out our atoms and how much we have of each of them. So I have carbon, I have hydrogen, and I have oxygen. Feels really simple, right? So why are these so difficult? Well, I'll show you. Okay, so carbon, we have 4, hydrogen, I have 10, and oxygen, I have 2. I still have carbon, hydrogen, and oxygen on this side. Okay, so carbon, I have 1, hydrogen, I have 2, and oxygen, I need to add up both of these oxygens, so I have 3 oxygen atoms. For combustion reactions specifically, it's best if you keep oxygen till the end. So I'm just going to write a little tip over here. For combustion, balance oxygen last. And there are actually 2 reasons why I want to balance oxygen last. First, it's always better as a rule of thumb to balance hydrogens and oxygens last. But specifically for combustion, why I like to balance it last is you can see oxygen here. I can put any number in front of my oxygen or my oxygen molecule, and I will only change oxygen. I'm not going to change any other atoms. So I like to save that one to the end, where hopefully I'm just trying to figure out how to balance my oxygens, and I'm not going to mess up any of my other atoms. So that's how I approach combustion reactions. Okay, so let's start with carbon, right? So my carbons are not balanced right now, but if I put a 4 here in front of my CO2, that changes that to 4, and now I have 8 oxygen plus that one there. Gives me 9 oxygen. I have to make sure I do my addition right. Okay, so next I'm going to balance my hydrogens. Again, I'm saving oxygen till the end. So I have 10 and 2, so if I put a 5 here in front of water, that should fix my hydrogen. So 5 times 2 is 10, and then I have some more oxygen. So now I have 4 times 2, which is 8, plus 5 gives me 13 oxygen. Okay, so everything is balanced except for oxygen, but I have 13 oxygen on my product side and 2 oxygen on my reactant side. So there isn't a whole number multiplier that I can use to balance my oxygen. So this is where I'm going to show you 2 different ways to do this. Sometimes, especially in combustion reactions, you might see a fraction. So what number could I put in front of my O2 to make that 13? Well, here, let me erase this so I can write it clearly. I can put 13 halves, because 13 halves, and I'll show it over here, 13 over 2 times 2 gives me 13. So this does give me 13 oxygen atoms, which gives me a balanced chemical equation. Now, there are a couple of problems with this, and it really depends on your professor or your teacher. We're not going to ever have half of an oxygen atom. Oxygen atoms only come in whole numbers. It's just like people. You're never going to have half of a person. You're going to have either a whole person there or you're not going to have a person there. So some people really do not like to balance with halves or balance with fractions at all. And so if that is the case, you need to then convert this to a whole number. So in order to convert this to a whole number, I'm going to multiply through by 2. So what I mean by that is I'm going to multiply each of my stoichiometric coefficients by 2. So I'm going to put a 2 here because, of course, we assumed it was just a 1. My 13 halves times 2, I'm going to erase this, just gives me straight up 13. 4 times 2 gives me 8, and 5 times 2 gives me a 10 here. Let's recount and make sure that my equation is still balanced. Okay, so for carbon, I now have 8 carbon atoms, I now have 20 hydrogen atoms, and I have 26 oxygen atoms. Okay, so for carbon on my product side, I have 8. For oxygens, I have 8 times 2, which is 16, plus 10 times 1, which is 10, which gives me 26 oxygen atoms. And for hydrogen atoms, I have 10 times 2, which is 20. So you can see I still have a balanced chemical equation. So if you're ever in a situation you feel like, wow, I really want to use a half, some kind of half here, like 13 halves or 5 halves, you can go ahead and use it. Again, if your teacher allows it, you can move forward with that. If you know that your professor is not such a fan of the halves, then just multiply everything through by 2. You should still have a balanced chemical equation, and it'll also eliminate that half, whatever that half is. Okay, let's make sure there are no questions. Let's move on. Yeah, okay, I'm just checking time. We've got time for some more. All right, so let's go on to these equations right here. Again, we're going to see some more fraction work as well. So starting with my iron one here on the right, let's just list out, atoms. Iron, oxygen, and hydrogen. Sometimes I really feel like it's these equations that just have a few atoms that are the most difficult to balance. Okay, so iron, we have 1, oxygen, we have 2. Oh, sorry, no, we don't have 2. See, I already missed it. I have 2 oxygen here, but I have to plus my 1 there. I actually have 3 oxygen atoms, and I have 2 hydrogen atoms. Okay, so for iron, oxygen, and hydrogen, I have 1 iron, I have 3 oxygen, and I have 3 hydrogen. So I'm like really, really close, right? But this is not balanced. Okay, so what I've really got to deal with are my hydrogens, and I'm going to do that kind of crisscross or flip-flop switch. So I'm going to put my multiplier of 3 over here in front of my water. And so what that does is that's going to make my hydrogens be 6 and my oxygens be 3, 4, 5. Okay, and then if I put a 2 here, again, because I'm flip-flopping, that's going to give me 2 iron. Okay, this is where it's tricky. We've got to be careful with our multipliers. So remember, this 3 multiplies to the oxygen and the hydrogen, but this 2 multiplies to the iron. Oops, that goes to the oxygen and to the hydrogen. So my oxygen and hydrogen have 2 multipliers, which means my oxygen is 3 times 2, which is 6. And the same thing for my hydrogen. It's 3 times 2, which is 6. Okay, I'm maybe a little bit closer. Let's fix my iron. So I can make this 2 by putting a 2 here. Okay, that's at least easy, and I haven't changed anything else. Again, I'm left with oxygen at the very end. So there are 2 different ways to approach this. I have 6 oxygen on my product side. I have 5 oxygen on my reactant side. I could do this with a half, but what I think is going to be better is to multiply everything through by 2. So let's make this all whole numbers, because if you balance with whole numbers, you're going to always be correct. But if you balance with fractions, sometimes, again, some people don't like that. So let's multiply through by 2. So this 2 is now 4. I'm still going to leave this oxygen alone for now because I'm not totally sure what goes in front of it. This 3 is going to be 6, and this 2 becomes 4. So let's add up what we've got right now. So my irons are now 4. My oxygens are 6, 7, 8, and my hydrogens are now 12. Okay, so over here, my irons are 4. Again, remember both of these multipliers. So my oxygen is 12 and my hydrogen is also 12. Again, I'm taking 4 times 3 right here. So you can see I'm really, really close. So I have 12 oxygen over here and I have 8 over here. So notice that I've already taken into account 6 of my oxygen right there. So I just need to bump this up to 12, which means if I do a 3 here, this is 3 times 2, this is 6, plus another 6 gives me 12 oxygen. Okay, so again, multiplying through by 2 is sometimes a great a handy tool to have. If you feel like, wait, there's a fraction here somewhere and I'm not sure where it's going or what's happening with it, it's probably some kind of half, and multiplying through by 2 can help get you back on the right track again. Okay, let's do our right-hand equation here with ammonia and oxygen. So same thing, I'm just going to list out my atoms, hydrogen and oxygen. And the same thing on the product side. And I need to not forget to count up my atoms. So nitrogen, I have 1, hydrogen, I have 3, oxygen, I have 2. Nitrogen, I've got 1, hydrogen, I have 2, and oxygen, I have 2. So again, you can see why we tend to put hydrogen and oxygen at the end of our balancing, because they are the ones I feel like that always create the problems. Okay, so because oxygen is all alone here, and I can put whatever number I want in front of this and hopefully balance the oxygens, I'm going to balance my hydrogens first. So again, I've got this 3 and 2 situation going on. So let's put my 2 here and my 3 here, and let's recount all my atoms. So now I have 2 nitrogen, I have 6 hydrogen, I still have 2 oxygen. I still have 1 nitrogen here, I have 3, 4 oxygen, and my hydrogen, I have 6. All right, so at least my hydrogens are balanced. So let me see if I can fix my nitrogens. If I put a 2 here, that's going to make this 2, but I've changed my oxygens. I have 2 plus 3, I have 5. Okay, so again, this is feeling like a fraction, because if I wanted to, I could put 5 halves in front of my O2. 5 halves, I'll just show it down here. 5 halves times 2 does give me 5 oxygen. So that would give me a balanced chemical equation, but it's a fraction. So let's multiply everything through by 2 and let's get our whole number balanced chemical equation. Okay, so this is no longer a 2, but this is a 4. My 5 halves becomes 5. My 2 here becomes a 4. And my 3 here becomes a 6. So let's just double check and make sure everything is balanced. So nitrogens, I now have 4. Hydrogens, I have 4 times 3, I've got 12. Oxygen, 5 times 2, I have 10. All right, nitrogens, I have 4. Hydrogen, 6 times 2 is 12. And oxygens, I have 4 plus 6, which is 10. Again, we multiplied through by 2, it made everything whole number. So if you're in that situation, you feel like, oh boy, either I think this is a half or I could balance with some kind of a half, just multiply everything through by 2. Okay, let's do just one more. This is going to be another difficult one, and then that will be it for tonight, I promise. Okay, so again, we have ammonia and oxygen, except this time we've got a methane thrown in there. Okay, so nitrogen, hydrogen, oxygen, carbon. Okay, so I have 1 nitrogen, 3, that's 7. Oxygen, I have 2. Carbon, I have 1. Same, I have nitrogen, hydrogen, oxygen, and carbon. Okay, 1, okay, that's 3 total, because 1 here and 2 here. I have 1 here, and carbon, I have 1 here. Okay, so what I'm seeing is except for, again, hydrogen and oxygen, I am balanced. But I have this, 2 to 1 here. You know what I think I'm going to do with this one? I am going to start by multiplying through by 2, maybe. Because why not? Maybe I'll start with a 2 here. Okay, so that would change my oxygen to 2, and that would change my hydrogen. This is 4 and 1. That would change it to 5. Again, so now I have this weird 5, 7 thing going on. So let's go ahead and start by multiplying everything through by 2. So I'm going to put a 2 in front of all of these, and this now becomes a 4. Because Why not, right? Okay, so this is nitrogen is now 2. Hydrogen is 6. Oh, no, sorry. This is 6 plus 8. That's 14. Oxygen is 4. Carbon is 2. Okay, so nitrogen. This is also 2. Hydrogen is now 2 plus 8, which is 10. Oxygen is 4. And carbon is 2. Okay, so you can see we're really, really, really close. All that is not balanced at this point is our hydrogen. But of course, to change hydrogen, we're going to have to change this oxygen here as well. So I am going to, let's see, this one, I think, what if I changed this to a 6? Let's see. Again, this one is a more difficult one. You can see I'm kind of going back and forth and thinking, what is going to make the most sense here? So that gives me 12, 13, 14 hydrogen. It gives me 6 oxygen. And so it doesn't change my carbons or my nitrogen. So can I balance it on this side? I know that this guy is going to definitely be wrong. So what have I got here? My hydrogens are balanced. So it's really just my oxygens, which means if I put a 3 in front of here, that's going to give me 6. So that is balanced. Okay, that one was definitely a doozy to balance. Okay, so yes, so you can see sometimes balancing equations is seen as a really simple thing, but it can be a challenge at times to get things balanced. What I also haven't done here is I haven't balanced any redox equations, which is a completely different method because you balance in either acidic or basic solutions. If that's something you would like to see, balancing redox equations where we have to write half reactions and balance charges and electrons first, then just let me know. We can certainly do that. But I hope that you can see that balancing equations is not always easy, but hopefully with these tips and tricks, I can make it just a little bit easier for you. Well, thanks so much for joining us in the new year. I hope to see you next week. And again, just let me know how we can best help you. Thanks so much. Bye.